In this video, we will discuss the electrophilic aromatic substitution reactions, EAS, of substituted benzenes. So this should actually be interesting. In the previous lesson, we learned just 6 reactions, and we only discussed those reactions to benzene. In electrophilic aromatic substitution reactions, a hydrogen on benzene was substituted with some electrophile. What the exact electrophile was varied. And though there was an overall substitution, this process proceeds via 2 elementary steps: electrophile addition, followed by an electrophile elimination step. In the electrophile addition, the electrophile is the active electrophile, the E+, and the electrophile elimination, that electrophile is proton, H+, and a net substitution occurs. We learned 6 electrophilic aromatic substitution reactions. First, bromination, using molecular bromine and iron 3 bromide to generate this active electrophile that reacted with benzene by the general mechanism shown to yield bromobenzene. We learned a second halogenation reaction, and that was chlorination by very similar conditions, just swapping out aluminum chloride for iron 3 bromide, generating chlorobenzene. In a different lecture, I will teach you how to generate iodo or fluorinated benzene, those 2 molecules being made by different types of reactions. Nitrobenzene was generated in a nitration reaction with nitric acid and sulfuric acid, generating this active electrophile, to which benzene added in an electrophile addition step, followed by an electrophile elimination step, as we've discussed in the general mechanism to generate this product. The final 3 reactions learned were sulfonation, alkylation, and acylation. Treatment with fuming sulfuric acid, which simply means that sulfur trioxide is present, generated the sulfonic acid from benzene via this active electrophile. The alkylation and acylation reactions are particularly exciting because carbon-carbon bonds were generated, forming alkyl benzenes or acyl benzenes, aka ketones. Both of these reactions involve aluminum chloride to generate the active electrophiles. For the alkylation, a carbocation, and for the acylation, an acylium ion. We discussed for the alkylation that the carbocation must be stable and not subject to undesired rearrangement. The acylation doesn't have any of those issues, and so we found that for many desired alkyl benzenes even, acylation provided a viable alternative to access them. We spent some time discussing how acyl benzenes, these ketones, could be reduced to generate alkyl benzenes. Please review those 4 reduction methods on your own in case you need them in synthesis problems today. Please be sure that you are familiar with and can draw out the general mechanism for electrophilic aromatic substitution reactions, as well as can provide the reagents, and remember all 6 of these reactions before you move on, because we'll be using these reactions today just to substituted benzenes. The learning goals for today are to identify common substituents as electron donating or electron withdrawing groups. We'll be abbreviating electron donating as EDG, electron withdrawing as EWG. And common substituents, I just simply mean functional groups that may be found on aromatic rings. We'll be discussing substituted benzenes today. So these Y groups, just a generic group. What are the common functional groups that may be on benzene rings? We will then predict the products of electrophilic aromatic substitution reactions of these benzene derivatives. So we'll be treating them under the same 6 reaction conditions that we just reviewed, and then we'll be predicting the products. So now there's going to be Y, the substituent that was there to begin with, and the substituted benzene. And then E will be somewhere as well. Now just quickly, when I draw these lines into the ring, it just means they're bonded to one of the carbons, and I'm not specifying which one. So that is what that convention means. You should be able to draw the complete curved arrow mechanisms for these electrophilic substitution reactions of benzene derivatives, and that'll be no problem because you already know how to do this for benzene. Finally, explain the selectivity of substitution reactions of benzene derivatives using clearly drawn resonance structures and reaction coordinate diagrams. We can do this. Let's just get to it. The first substituted benzene that we will consider today is called anisole. Anisole is methoxybenzene. And we should be intentional about thinking about what type of substituent this is. Methoxy is an alkoxy group, or OR. So although we are considering the nitration reaction of anisole, what we learn might be general to alkoxy benzenes. Pause, predict, and name the possible products of this reaction. All 6 carbons of benzene are the same due to the symmetry in that molecule. So when benzene undergoes nitration, we just pick one of these 6 carbons and substitute the nitro group for hydrogen. Anisole does have a plane of symmetry running through the middle of the molecule. And yes, this because there's free rotation around this carbon-oxygen bond, so there is a plane of symmetry there. Now, that means that there are 3 possible unique positions where this nitration can happen. It can happen here, which is the same as here, and this position is called ortho. It is adjacent or has a 1-2 relationship to the existing substituent, methoxy. There is the carbon that has a 1-3 relationship to the methoxy, and there's 2 equivalent carbons that have that relationship. That carbon is called the metacarbon. And then finally, there is 1 carbon that has this 1-4 relationship to the existing alkoxy group, and that is called the para position, P. We might expect that substitution could happen at any of those 3 positions. Substitution at the ortho position would lead to orthonitroanisole. Substitution at the meta position in this 1-3 relationship to the existing alkoxy group results in meta-nitroanisole. The third and final unique possible product formed by electrophilic aromatic substitution is para-nitroanisole. And if you're wondering, well, why can't there be substitution of nitro in place of the methoxy? Well, remember, methoxy would have to leave in an electrophile elimination step without its electrons. So it would leave like this. How does that look? Yeah, that looks horrible, very high energy. So we're not going to have substitution at the 1 carbon because that would make a really high energy electrophile. All right, so that's not going to happen. So that's why we're only considering the carbons that have hydrogens because they can leave as proton, H+, and that is okay. That is low energy. Now we should predict the relative ratios of these products. So just go ahead, predict what you think the relative ratios of these 3 possible substitution products would be. Well, as we discussed, there are 2 ortho positions, right? 1, 2, due to the symmetry in the molecule. There are 2 meta positions due to the symmetry in the molecule. And there is 1 para position. So statistics would suggest that these 3 products are formed in a 2-to-2-to-1 ratio. And if we're going to consider percentages, which we are, that would be 40% orthonitroanisole, 40% meta, and 20% para. All right, that is our prediction just based on statistics. Let's compare this prediction with the observed result. The observed result is when anisole is nitrated, the ortho and para products are the only observed products. And in fact, the para product is the major product. Wait a second. That is not what we predicted here, right? We thought the para product would be the minor because there's only 1 para position. And we thought that the meta product would be formed. So this is weird or unexpected, maybe is a better word to use. So how can we explain the observed product ratios? Well, we're going to explain it through the mechanism. And I did want to mention, just be sure that you don't forget how to draw out the nitro group. I know we often, almost always, abbreviate the nitro group, but be sure that you can draw the Lewis structure for nitro. All right, now I suggest that you draw the complete curved arrow mechanisms for the formation of all 3 products, even the meta, even though it's not formed, so we can understand this observed product ratio. All right, be sure that you've done this. I've written out most of the mechanisms for the formation of all 3 possible products, even the meta product, which is not observed. First up, pi electrons from the ring will react with electrophilic NO2 plus. These curved arrows can be used for both the ortho and the meta intermediates. So here are the two atoms to which the carbon-nitrogen bond can be formed. To form the ortho product, this atom forms the bond to nitrogen. To form the meta intermediate, this carbon right here is forming the bond to nitro. The curved arrows for forming the para-intermediate are similar. Now just draw those electrons, and then this carbon makes a bond to nitro. Now this first step, the electrophile addition step, is the slow step in this reaction. It is the rate determining step. That means the relative energies of these intermediates determines the product ratio. It determines how fast the reactions are. So we need to think about the relative energies of these intermediates now. We have discussed these intermediates before. We said they're non-aromatic and stabilized by delocalization of charge. So although you do see I have written the curved arrows for the second electrophile elimination step for forming all these products, let's just take a moment and think about how these intermediates are stabilized by delocalization of charge. When we discussed the electrophilic aromatic substitution reactions of benzene, we drew out 3 resonance structures that described how the non-aromatic species was stabilized by delocalization of charge. These same resonance structures, 2 each, can be drawn for the intermediates in the ortho, meta, and para substitution reactions of anisole. Thinking about these intermediates, we notice that for the ortho intermediate, especially in this resonance structure, when we consider the lone pairs of the methoxy group, there's one additional resonance structure that can be drawn and shows how the charge can be shared by oxygen as well as the carbons in the ring. Looking down at the para intermediate, we can see the same situation or a very similar situation where there's a resonance structure where methoxy is lone pairs or adjacent to a positive charge. So we could draw an additional resonance structure. And I'll show the curved arrows from here for convenience sake, but it doesn't particularly matter. So we can draw this additional resonance structure that shows how the methoxy group directly shares the positive charge with the carbon atoms of the ring. Now, take a look for the meta intermediate. Can you draw a similar resonance structure? No, you can try, but you cannot. So we cannot draw a similar resonance structure where the electrons from oxygen are delocalized into the ring and all atoms have filled octets, such as the case for these 2 resonance structures. And because of this, the meta intermediate is higher energy than the ortho and para intermediates, which are stabilized by these additional delocalization of charge. Because this first step is the slow step and the meta intermediate is so much higher energy, the meta product is not observed. We want to come back to this slide to explain why the para product is the major product, because we haven't explained that yet. But let's take what we've just discussed and translate it to a reaction coordinate diagram. Electrophilic aromatic substitution represents a 2-step process, electrophile addition and electrophile elimination. So we expect a reaction coordinate diagram to look like one of these pictures. There are 2 transition states, telling me there are 2 steps, and then 1 intermediate. So the reaction coordinate diagram that I've started to draw down here will look like one of these 2 pictures. The thing we must decide now is, will there be a larger activation barrier for the first step in our reaction coordinate diagram or for the second step? Yes, on the left, there is a slow first step and a fast second step. On the right, smaller activation barrier for the first step, so a fast first step and a slow second step. Yeah, so our reaction coordinate diagram will look like this one, because the electrophile addition step to generate the non-aromatic cationic intermediate is the slow step for this reaction. So I've started to draw out this reaction coordinate diagram for the nitration of anisole. And now I need to decide which of the three intermediates correspond to each curve in the diagram. Yeah, the highest intermediate is the meta-intermediate, which is not shown here in this scheme since that product wasn't observed, but let's go ahead and include it anyway, because remember, this diagram is meant to explain why it is not observed. Now, the other two intermediates, ortho and para, I have put them with different energies. So what do you think is lower energy, the ortho intermediate or the para? Yeah, the para is the major product, so it is lower energy than the ortho intermediate. Now, we haven't discussed why that is yet. Perhaps now is a good time, but we can tell from the results, especially since they're inconsistent with what we'd expect statistically, the para is lower energy. That intermediate is lower energy than the ortho. The para-intermediate is just slightly lower energy than the ortho-intermediate because there is a little bit of steric interaction between the methoxy and the nitro group. So that little bit of steric clash, overlap of electron clouds in space, makes the ortho-intermediate just a bit higher energy. And thus, the para product is observed as the major product. Since the meta-intermediate is so high energy, it's the slowest of form and not observed. The product resulting from it is not observed. Okay, and the second step is fast for all of these. So we don't really care about the second step because it doesn't affect the relative product ratio. We'll draw it in anyway. Now we have used a reaction coordinate diagram to explain why, when anisole is reacted under nitration conditions, only the ortho and para substitution products are formed, where the para product is the major product. This is primarily due to additional stabilization of charge that the ortho and para intermediates have that the meta intermediate does not have, making it higher energy. The para product is observed in a higher amount than the ortho product, even though there's only one para position while there are two ortho positions. So statistically, that was a bit confusing, but we can rationalize this observation with the steric interaction between the methoxy group and the nitro group in this intermediate when the nitro group is ortho to the methoxy. That steric interaction makes this ortho intermediate a little bit higher energy than the para, and thus the para product is the major product, even though both products are observed. The methoxy group of anisole is called a directing group. It directed where this electrophile added. It directed where the nitro group added. Because methoxy was present, only the ortho and para products were formed, not the meta product. Methoxy is said to direct the second substitution. And luckily, there will be some patterns for how directing groups determine the constitutional isomer of the product of the second electrophilic aromatic substitution, and we're going to learn those patterns in a minute. First, let's draw all the resonance structures of anisole, so all the unique resonance structures of anisole, methoxy, benzene. We could shift the electrons around the ring, I suppose that would be fun, but that does not represent a unique resonance structure because it's an equivalent resonance structure to this one. So let's go ahead and draw some different resonance structures here so that we can understand what they tell us about the electronic structure of anisole. So there's one. Let's move these electrons down here, move them on there. Those curved arrows result in this resonance structure. And then we'll draw one more, but as you are going to recognize, this last one that we're going to draw is equivalent to this resonance structure. Of course, the major resonance structure is represented by the two neutral resonance structures. So these are the major resonance structures. And we can even show a composite of these two neutral resonance structures by just drawing the circle. All right, so that's definitely the major resonance structure. And these resonance structures represent minor, but contributing to minor resonance forms. And what those minor resonance structures inform us is that the ortho and para carbons are electron rich. So I'm going to put that on this major resonance structure. The ortho and para carbons are electron rich. This analysis gives us another way of understanding why, when anisole is treated under electrophilic aromatic substitution conditions, that methoxy substituent will direct the electrophile to the para and ortho positions. Think about the role of the aromatic molecule in electrophilic aromatic substitution. The role of the arene is as a nucleophile, as the electron-rich species, and the ortho and para carbons are more electron-rich than the metacarbons, as demonstrated by these minor resonance structures. And so the ortho and para products are observed. We rationalize this observation by considering the stabilities of the intermediates leading to each of the different products. And that analysis is correct in one way to think about it. And another way to understand what's happening is an analysis of the starting material. So we have two ways of understanding why methoxybenzene, when it undergoes this electrophilic aromatic substitution reaction, will direct that electrophile to the ortho and para positions. And I have a secret for you. This will be general. So when a benzene ring is substituted with an electron donating group, we will expect that if it is subjected to electrophilic aromatic substitution reactions, the ortho and para substituted products, those constitutional isomers, will be observed, will be favored relative to the meta product, which will typically not be observed. All right, pause and be sure that you can summarize what we have just learned on the past two slides. Now, in contrast to methoxybenzene, when acetophenone is nitrated, the meta product is the observed product. In other words, although you can certainly write a mechanism that would show the formation, and it seems 100% reasonable that the ortho and the para product could be formed in this process, just like it seemed reasonable that the meta product would have been formed for methoxybenzene, the ortho and para products are not observed in the nitration of acetophenone. How can we understand this observation? Similar to how we analyze methoxybenzene anisole, there are two ways that we can rationalize this observation. And the first is just by thinking about the resonance structures of the starting material and how they might relate to the nucleophilicity of the individual carbons of the substituted benzene ring. Now, first of all, one big difference between methoxybenzene and acetophenone is that this acyl group is actually an electron withdrawing group. All right, how do I know that? Well, I'll tell you what the pattern I'm looking for in a moment, but just right now, let's just draw resonance structures. We know we can because there are adjacent pi bonds. So when there's adjacent pi bonds, we know that we can draw resonance structures, and this is one big conjugated pi system. All those adjacent sp2 hybridized atoms. So we know that there should be several resonance structures that can be drawn for this molecule. So I've gotten started as usual while I'm talking, but you should pause and see if you can draw the rest of these resonance structures, maybe even try to explain how the resonance structures relate to the observed product before I get to it. Okay, we can keep moving the electrons around the ring here. One more time. So these resonance structures clearly show how the acyl group is an electron withdrawing group. We pushed electrons out of the ring and into the carbonyl. And yes, these two resonance structures here are equivalent. The ortho and para carbons are electron poor. That will generally be the case when there's an electron withdrawing group on the benzene ring. And that is the opposite of what we saw for electron donating groups on the benzene ring. We saw that the ortho and para positions were electron rich. When they were electron rich, they reacted. When they were electron poor, they do not react with the electrophile. The meta position reacts. So the ortho and the para positions are electron poor. That leaves the metacarbon, these two equivalent metacarbons. The metacarbon is the most electron-rich carbon atom, having a proton to lose in the electrophilic aromatic substitution, and so the meta product is observed. Great, so we've explained this with thinking about the starting material. We would also like to explain this observation based on the relative stabilities of the three possible intermediates, just as we did in the case of anisole. Because the electrophile addition is the rate determining step of the nitration reaction, the relative energies of these intermediates will determine the relative rates of the formations of the products derived from each of these intermediates. That's a mouthful. Now, I've drawn each of the three possible intermediates here. And of course, just to mention this one more time, since there are two meta positions, each of those react. So you would have this, and you'd have where the other metacarbon react, but they're the same molecule. They're equivalent. So I've only just showed one. So when I say there's three positions, I mean the ortho, the meta, and the para. And there's two orthos, and there's two metas, okay? But I don't need to show every single carbon reacting because the two orthocarbons make an equivalent intermediate, the two metacarbons make an equivalent intermediate. Okay, moving on from here. Now, we probably want to think about the resonance structures that describe this non-aromatic delocalized cation. So if you haven't already drawn them out, please go ahead and do so now. So each of the intermediates can be described by a total of three resonance structures. And, with the methoxybenzene, there was this aha moment where we saw there was an additional fourth resonance structure for both the ortho and the para intermediates, but not for the meta. That's not the case for these nitration intermediates of acetophenone. So the explanation just lies in the resonance structures we've already drawn. And there is one we kind of forgot or neglected to draw, and that's this resonance structure, where the electrons in the carbonyl of acetophenone are just localized on the oxygen carbon, and then there's a positive charge on the carbonyl carbon. This resonance structure, is how we rationalize why carbonyls are electrophilic. There's a partial positive on the carbonyl carbon. So now, let's just go in and put that partial positive on all these carbonyl carbons. And when you see something here, just give a shout. Oh, wait, I'm not there to hear it. Okay, what do we see? Pause if you want to try to look for it. So for the ortho intermediate and for the para intermediate, there are these resonance structures that have a positive formal charge on the aromatic carbon adjacent to the partial positive of the carbonyl carbon. Yikes, like charges repel. So because the localization of charge is not as stabilizing for the ortho and para intermediates, right? Since that delocalization of that charge puts these partial positives on adjacent atoms. The ortho and para intermediates are higher energy than the meta intermediate. We'll try to squeeze that into a reaction coordinate diagram somewhere. So we have the same starting material, that's acetophenone. The meta intermediate might be here, and the ortho and para intermediates are a higher energy because they're not as stabilized by the localization of charge. So the activation barrier to forming the ortho and para intermediates, which would result in these products, is higher. And thus, the products resulting from those intermediates are not observed. All right, be sure that you've got this down and you can explain it to a friend or your reflection or your plant or whatever. And then we're going to summarize and generalize. This is an important slide, but it also is going to contain a lot of information. So we just want to make sure that we understand what is trying to be conveyed. So far we have learned that when a substituted benzene is treated with an electrophile, the nature of the substituent, if it's an electron donating group or an electron withdrawing group, it will determine which constitutional isomers of the product are observed and in what ratio. Typically, when Y is an electron donating group, the ortho and para products are observed. When Y is an electron withdrawing group, the meta product is observed. That's what we've learned so far. But it's not exactly that simple because there are different types of electron donating and electron withdrawing effects, and there's a balance and an interplay between them. So there can be inductive effects. So through the sigma framework, by inductive, we mean electronegativity. So let's write that in here on our chart. So I'm going to write electronegativity. Now, electronegative atoms withdraw electron density through the sigma framework. And then there's effects that we describe by resonance structures. Those are pi effects. Different substituents are going to have different inductive and resonance effects. So we're going to go through and we're going to think about all the different possible Y groups, of course not all, but the most common ones, and whether or not they are inductive withdrawing groups or donating groups, and whether or not they're resonance donating groups or withdrawing groups. These electronic effects will determine the direction of the electrophilic aromatic substitution reaction of these substituted benzenes. In particular, the pi effects are the main factor for determining the direction. And then the balance between overall electron withdrawing and electron donating effects over both types of sigma and pi overall, that will determine whether or not the substituted benzene will react at a rate faster than benzene. So that would be activated. It reacts faster than benzene, or react slower than benzene. So faster than benzene, that'll be for molecules that are more electron rich. Deactivated substituted benzenes will react slower than benzene, and they'll be electron poor relative to benzene. So let's go through now, group by group, and discuss the electronic effects of that group. We'll start with the amino group. So where Y is NR2. Here I have an example. I've put methyl groups, but it really is general to NR2. Because nitrogen is more electronegative than carbon, the amino group is an inductive withdrawing group. It withdraws electrons through the sigma framework. However, there's that lone pair of electrons, and that lone pair of electrons, here, let's draw it up here on Y, it can be donated to the ring, and we can draw resonance structures that demonstrate that, right? The nitrogen from the amino group is conjugated to the pi system of the ring, and those electrons can be donated. And I have done you the favor of looking through lots of data. And what I'm going to do is I'm going to use W's and D's to represent the magnitude of the electronic effect. So nitrogen is a mild withdrawing group through the inductive framework, and it is a really good donor through the pi framework. So 4 D's. All right, and now that resonance effect, it determines the direction of electrophilic aromatic substitution reactions of amino benzenes. Typically, the ortho-para products are expected because the ortho and para carbons are more electron rich, as we discussed in the case of methoxybenzene, anisole, and then also the intermediates resulting from electrophilic aromatic substitution at the ortho and para carbons will be stabilized with the electrons that nitrogen can donate. Awesome. Now, thinking about whether or not aminobenzene will react faster or slower than benzene itself, we need to think about overall, will aminobenzene be more or less electron rich than benzene? Well, it has a really, really strong electron donating group. So it is overall more electron rich than benzene, and so it is activated. It will react faster. Next, we will discuss hydroxy. And the same discussion applies for alkoxy, where the hydrogen is swapped for an alkyl group. Of course, we have discussed alkoxy already in the context of methoxybenzene. Now, oxygen is more electronegative than carbon, and it's more electronegative than oxygen. So we're going to give it 2 W's for its sigma effects, for its inductive effects. It's a good inductive withdrawing group. Oxygen is very electronegative. Oxygen has lone pairs, when adjacent to the ring, it is conjugated to the pi system of the ring. So oxygen, the oxygen in hydroxy or alkoxy is a resonance donating group. But because oxygen is a bit more electronegative than nitrogen, we're going to give it 3 Ds. So it's really donating to the pi system, not quite as donating as nitrogen. Now, the fact that it is donating through the pi system means that if an electrophilic aromatic substitution reaction is conducted on phenol, that existing pi donor will direct the electrophile to add in the ortho and para positions. So it is an ortho-para director. Now we do see that overall the alkoxy group or the hydroxy group is more donating than withdrawing. It's a pi donor, 3 Ds. Again, this comes from data. I'm just sparing you the data. It'll take us a long time to go through it. So that means that phenol or methoxybenzene, alkoxybenzenes are activated. They will react faster than benzene in electrophilic aromatic substitution reactions. On to alkyl groups. We've already discussed alkyl groups when we discussed the Friedel-Crafts alkylation. Because the carbon of the alkyl group is carbon and the atoms in the ring are carbon, there are no significant inductive effects for the alkyl group. But the alkyl group is an electron donating group via hyperconjugation. When we discussed this in the context of the Friedel-Crafts alkylation, I drew out hyperconjugation as it stabilizes carbocations. But I can draw out hyperconjugation as it applies to the aromatic ring as well. Here's a pi system of the aromatic ring, and I'll just put in how I drew the p orbital for a carbocation. So we're going to look at donation to the ring, so in the context of today's lesson, and then in the context of cation stability, just so you have something to compare with. Okay, if there's a methyl group adjacent to the ring, so on this Y position, although there is free rotation around that carbon-carbon bond, a methyl group or any alkyl group, so I'm drawing sigma CH because it's a methyl group, but if this was another alkyl group, you do sigma CC or the other sigma CHs. But sigma CH has a really similar symmetry to the p orbital. Right? They look similar. And there are some empty pi orbitals. They're anti-bonding, but there are empty pi orbitals. And as sigma CH is filled, it can overlap with those empty orbitals. You might say, oh, but it's filling an antibonding orbital. Yeah, but these electrons in this bond are stabilized, and this is a very small interaction. So overall, this interaction is stabilizing because electrons are delocalized, and this donation makes the ring more electron rich, just like in the case of a carbocation, this donation stabilized the empty orbital because it delocalized the electrons in the sigma CH bond and also shared the charge bit. So hyperconjugation is a stabilizing effect, and most importantly to us today, it makes this ring more electron rich. The consequences of which are that alkyl groups are ortho-para directors. And because overall the alkyl benzene is more electron rich than benzene, it will react faster. And again, we've talked about this. That's why there's over-alkylation in the Friedel-Crafts reaction. Because alkyl benzenes react in electrophilic aromatic substitution reactions at a faster rate than just benzene. It's more nucleophilic with this electron donating group. Okay, it's about to get fun here. Let's think about a halogen substituent, such as chlorine. Now, as far as inductive effects, chlorine is quite electronegative, and so 2 Ws, similar to oxygen. Now, for pi effects, chlorine is in row 3 of the periodic table, carbon is in row 2. Also, chlorine is quite electronegative. So there is very little pi overlap between chlorine and the carbons in the ring. However, there is a little bit of overlap. So we'll put 1D. So a little bit of overlap, a little bit of pi effects. And I'll just write third row so you can remember why that is, that there is just a little bit of donation. But because it is a pi donor, particularly in the cationic intermediate of the EAS reaction, halogens are ortho-para directors in electrophilic aromatic substitution reactions. However, now we're thinking about activating versus deactivating. So will chlorobenzene react faster or slower than benzene? We'll take a look at the inductive and resonance effects, so the sigma and pi effects for chlorine. Chlorine is a very strong inductive withdrawing group and a little bit of a pi donor. So overall, the withdrawing effects are more significant in terms of rate. So chlorobenzene is deactivated. It will react slower than benzene in electrophilic aromatic substitution reactions where the ring is acting as a nucleophile. Chlorobenzene is just less electron rich because of the inductive effects of the electronegative chlorine atom. Let's look at a pattern before we move on. So these first four groups were pi donors, and they all, except for the alkyl, they all have something in common, and it's that lone pair of electrons on the heteroatom. That lone pair of electrons, like we have up here in the generic substituted benzene, that lone pair is conjugated to the pi system of the ring since it is adjacent, and that made these four groups pi donors, which resulted in orthopara direction and the electrophilic aromatic substitution reactions of those substituted benzenes. Let's draw out the next several functional groups. So there's an ester, a nitrile, an ammonium. We don't really need to draw that one out. And nitro. Nitro group is pretty common in aromatic chemistry, which we've discussed, but we'll continue to discuss. We'll continue to see how common the nitro group is. One thing that three of these four groups have in common now is that a pi bond will be adjacent to the ring. That's not the case for ammonium, but it is the case for the ester, the nitrile, and the nitro. There will be a pi bond adjacent to the ring. In contrast to the electron donating groups, which had lone pairs adjacent to the ring. We'll just draw out one example. Actually, just draw out an example that's not here, which is this acyl group, this ketone. It's going to behave just the same or similarly to the ester. We already saw acetophenone, and we already saw that the ketone, the carbonyl, was an electron withdrawing group, and that we could draw several resonance structures that showed how that functional group withdrew electron density from the ring, making in particular the ortho and para carbons electron poor. And so we saw direction at the meta position, and that will be the same for these four electron withdrawing groups. Thinking about the ester has few electronegative atoms, so it is an inductive withdrawing group. We'll give it 1W. It is also a pi withdrawing group in the same way that the acyl group was for the ketone. You can draw those resonance structures out. Because it is an electron withdrawing group, it will direct to the meta position, and electrophilic aromatic substitution reactions of ketones or esters that are directly conjugated to the ring will occur in a meta position. And they will occur with a slower rate than the equivalent electrophilic aromatic substitution reaction of benzene, because it is less electron rich. And I will not make you listen to me repeat that for nitrile and for nitro. I will, however, draw out one resonance structure each for nitrile and nitro to show you how they are pi withdrawing groups. Nitrile first. Here you can see that the orthocarbon is electron poor, as described by this resonance structure, and you can draw two other resonance structures that show how the other orthocarbon is electron poor and the paracarbon is electron poor. You will draw those out on your own. For nitrobenzene, I will show how the paracarbon is made electron poor. That will be this resonance structure, and you can draw the two others on your own. Okay, now the ammonium group is a bit more tricky, I suppose, but not really. There's this nitrogen with a positive formal charge that makes it an electron withdrawing group through the sigma framework. So W, there are no pi effects. It doesn't have a pair of electrons anymore to donate, so there are no pi effects. But because it is an electron withdrawing group, it does direct to the meta position, and it is deactivated relative to benzene. All right, be sure that you have this chart completed and that you understand it before moving on, because we are about to use it in some practice problems. So pause and predict the products of each of the following reactions. So these are reactions to benzene here, but there are two different electrophilic aromatic substitution reactions. So the product of the first reaction will determine which carbon the electrophile in the second reaction adds to, right? Substituents on benzene rings have directing effects. Either they'll generate ortho-para products or meta. All right, take a moment. Step 1 is a nitration reaction of benzene to generate nitrobenzene. The second step represents the bromination of nitrobenzene. And because the nitro that is there, it will affect what constitutional isomer of product is formed. Bromine could add ortho, meta, or para to the existing nitro group. Recall that ortho means a 1-2 relationship, where the existing substituent is at carbon 1. Meta means a 1-3 relationship. And finally, para means a 1-4. So 1, 2, 3, 4 relationship. Because nitro is an electron withdrawing group, it directs to the meta position, as we have discussed in our summary slide, and for the same reasons that acetophenone directed to the meta position. Because the ortho and para carbons are electron poor for nitrobenzene, just like they were for acetophenone. And because the intermediates leading to the ortho and para products, their electronic structures but higher energy, because the electronic structure of the intermediate has some partial positive character on adjacent carbons. Now, of course, for nitrobenzene, that resonance structure looks a bit different, right? There's a nitro, there's a bromine, but if bromine adds to the ortho carbon, then that intermediate is partially described by this high energy resonance structure. Okay, so it doesn't, is the bottom line, and bromine adds to the metacarbon because that intermediate is lower energy, and that carbon is more electron rich than the ortho and para carbons. And so the final product is this disubstituted benzene, where the two substituents have a meta relationship, a 1-3 relationship, due to the directing effects of the nitro, which was added first. Now, taking a look at the next reaction, they're the same sets of reaction conditions, but they're flip-flopped relative to the first problem that we looked at. So in step 1 now, there's bromination, which would generate bromobenzene. Bromo is a sigma withdrawing group, but a pi donating group. And the pi effects determine the direction of the next electrophile, which would be nitro, because there's a nitration. Bromine is an ortho-para director, which we have cataloged in the chart. Right? So instead of chlorine, bromine, we have halogen here because this is general. Right? So there's going to be a mixture of the ortho and para products. So what these two problems demonstrate is that the order in which the electrophilic aromatic substitutions are carried out determines what constitutional isomer of product is formed. These three molecules are constitutional isomers. If nitration is first, the meta isomer is formed. If bromination is first, the ortho and para isomers are formed, and you could probably separate these with a thin layer chromatography or some other separation technique in lab. Looking at the next two problems, we see that an electrophilic aromatic substitution reaction will be occurring, chlorination, on a substituted benzene. So we need to ask ourselves, is this an electron donating group or an electron withdrawing group? Well, the ketone, the acyl group, is an electron withdrawing group. There is a pi bond adjacent to the ring, and it is going to withdraw electron density out of the ring, as we've discussed. Thus, the chlorination will take place with meta direction, and only that constitutional isomer of the product is observed. This alkyl benzene is also subjected to chlorination conditions, but because alkyl groups are electron donating groups, all right, alkyl groups, electron donating groups, the ortho and para products will be observed. And actually, because this isopropyl is so large, just like we saw for anisole at the very beginning. It's obscured now, but it says para-product, major product. And we said that the para-product was the major product over the ortho because the methoxy group was large and it blocked sterically the ortho position from undergoing substitution. Some of the ortho carbon participated in the reaction, but the para-product was the major product. This observation can be explained in a similar way. The isopropyl group is quite large and its electron cloud blocks the substitution at the ortho carbon. So when the existing substituent is large, like an isopropyl group, a large alkyl group, or methoxy, then oftentimes the para product is the major product over the ortho, even though you might expect them both since alkyl groups are donating and they're ortho para directors. You can just contrast this to when bromobenzene underwent nitration. This single atom, bromine, is not very large relative to the many atoms of the isopropyl group. And so because of that, because bromine is smaller, its electron cloud is smaller than isopropyl, we did see a mixture of ortho and para products. Using what you learned in these problems, let's try some synthesis problems. Propose a synthesis for the following molecule from benzene. Really try and give it a shot. I know we're at the end of a long video, but come back and do it tomorrow and then finish up or just take a break. But please do pause and give this problem a try. Benzene is the given starting material for this reaction. So we know that these two bonds are made in this process. Now, this substituent looks great for Friedel-Crafts, or ideal for Friedel-Crafts alkylation, because this tertiary cation is stable and will not rearrange. Okay, so we're feeling good about Friedel-Crafts alkylation to make that carbon-carbon bond to the T-butyl group. However, this carbon-carbon bond, I'm pretty sure that is not going to come from a Friedel-Crafts alkylation, and that's because this secondary cation could almost certainly rearrange. You might say, well, but this is just going to make another secondary cation. Yes, it is, but cations are high energy and they're prone to rearrangement, and this cation might rearrange. And if it does, it's going to make this cation, and then if that adds to the benzene ring, it's not going to give the product that is desired. So I do not think Friedel-Crafts alkylation will work for this second carbon-carbon bond formation. That's okay, because there's another issue that comes up here. Since there will be two electrophilic aromatic substitution reactions, the first one will direct the second one. And we can see that the two groups have a meta relationship. And alkyl groups, they're ortho-para directors. So currently we have two ortho-para directors, but they have a meta relationship. So that is just another signal to me that this was not always an alkyl group. It perhaps was some meta director. We only have one choice, right? We only have one choice because we only know two ways to make carbon-carbon bonds right now to benzene rings and electrophilic aromatic substitution reactions. Friedel-Crafts alkylation with stable carbocations, and then Friedel-Crafts acylation with acid chlorides that generate acylium ions. And then we do know that if the ketone functional group is undesired, it can be removed or you can react with it further. So in the case here, we're going to need to add this methyl group. So we're going to want a 1, 2, 3, 4 carbon acid chloride. And because these two bonds need to be generated in a meta fashion, I'm going to add the acyl group first because it is a meta director. So I'm going to do the Friedel-Crafts acylation before the alkylation. Okay, I have that 4 carbon acid chloride and then aluminum chloride. The Friedel-Crafts acylation will generate this ketone. And then yes, I do think that we need to add this methyl group via a Grignard reaction and then do some other fancy footwork to generate this alkyl group. But before we do any of that, let's just add the T-butyl group because right now we have a meta director. The acyl group is an electron withdrawing group and it is a meta director. And once we convert it into the alkyl group, it's no longer going to be a meta director. So let's exploit its direction right now. Okay, so now to install the T-butyl group, we will, as I drew out at the top of the page, use T-butyl chloride. And of course, T-butyl bromide would be okay as well, with an equivalent of aluminum chloride. Because the existing acyl group is an electron withdrawing group, the T-butyl group will be directed to the meta position relative to it. All right, we have a couple of options here, actually 2 options. I had mentioned Grignard to add the methyl group, so let's try that, but you may have thought of a different way to add this methyl group and integrate that methyl group into the final product. But let's go ahead and use the Grignard route first. So methyl magnesium bromide followed by an aqueous workup. Now we have added the methyl group, but there's this alcohol functionality that is undesired. So we'll remove that with an E1 reaction. If for some reason you are afraid that the carbocation in the E1 is going to rearrange, you could use an E2. So you can make this a good leaving group, either a tosylate or PBr3 to make a bromide, and then eliminate with a strong base. No rearrangement really is plausible here, so I'm not going to worry about using an E2 pathway. And the alkene that results from the E1 elimination can be converted to the desired alkane with hydrogenation. Wonderful. Well, some of you may have said, how about the Wittig reaction to generate the methyl group? Yes. And not really the methyl group, but you can add a methylene here, generate an alkene. And then that alkene can be hydrogenated to the final product. Right, 2 routes to this final desired product, starting from benzene. Really the most important part of this problem is that there's 2 electrophilic aromatic substitution reactions, and we must acylate first because acyl is a meta director. But if we had alkylated first, the alkyl group is a para director. So there would be no way to get the observed relationship if we had alkylated first. So we had alkylated and then added an acid chloride for Friedel-Crafts acylation. The para product would be observed. Really no ortho because the T-butyl group is huge and it blocks the ortho position. Okay, this is not the desired constitutional isomer, so we had to acylate first. Good, let's try another problem. Propose a synthesis of this molecule from benzene. Pause and give it a try. The product is a disubstituted benzene. We know that these 2 bonds will be made. First things first, look at the relationship that is desired for the substituents in the product. So they have a para relationship. However, nitro is a meta director. It is an electron withdrawing group. Alkyl, however, is electron donating, and it is an ortho-para director. This is a pretty bulky alkyl group, so we would expect that the para product predominates over the ortho product due to steric blocking of the ortho position by that big group. All right, so that means we're going to add this alkyl group first, since it directs ortho-para, and we do expect para to predominate because it's so big, and there's a para relationship in the desired product. We will install alkyl first. To make this carbon-carbon bond, there are 2 choices, Friedel-Crafts alkylation and Friedel-Crafts acylation. Friedel-Crafts acylation would look like this, where these carbons come from this acid chloride. Friedel-Crafts alkylation, on the other hand, would look like this. In the proposed alkylation, the alkyl group comes from a primary cation adjacent to a quaternary carbon. Now, this would immediately rearrange to generate a tertiary carbocation, which is more stable and would not lead to the desired product. It would lead to an alkyl group like that. That's fine, but that's not the desired alkyl group. So we're not using Friedel-Crafts alkylation. We will use Friedel-Crafts acylation. Now from here, 2 things need to happen to generate the final product. Carbonyl should be reduced. In the product, it's not there. Right? Look at the product. It's an alkyl group. And then the second thing that should occur is a nitro group that should be installed. All right, now, if nitration was conducted at this stage to the ketone, so if we tried to install the nitro group now, what would happen is the acyl group is electron withdrawing. It is a meta director, and this undesired constitutional isomer would be formed. Meta relationship, whereas there's a para relationship in the desired product. So it's not time to nitrate. It's time to reduce that carbonyl. So we will do that first. And once the alkyl group is formed, then we will nitrate. The alkyl group is an orthopara director. So that will work out for us. Now, this is not a very sensitive molecule, so you could use any of the 4 reduction methods that were discussed in the previous lecture for reducing ketones to alkanes. Right? This is a pretty big reduction occurring here. I have just chosen the thioacetal method because I like it. So although the carbonyl must be reduced first, and then we'll add the nitro group, any of the 4 reduction methods would have been appropriate here. And if you don't remember what those are, you need to pause, get your notes out, and go look at those 4 reduction methods at the very end of the last lesson. Now the alkyl group has been installed, and it is an orthopara director, although because it's so large, it is going to really favor the para position. Now the nitro group can be installed. Treat with nitric acid in the presence of sulfuric acid, and the desired product will be formed. The sequencing of these steps is important. It is also important that acylation was used and not alkylation. So acylation needed to be used, and then the carbonyl needed to be reduced to form an orthopara director, and that's related to the fact that you could not have nitrated first, because if you had nitrated first to generate nitrobenzene, and then try to do the Friedel-Crafts acylation, this would not work. First of all, this is a very unreactive ring, but if you force it, you can get it to acylate, but the nitro group is going to direct to the meta position. So we would not get the desired para constitutional isomer. The product would get this undesired meta. So that's important to keep in mind. The order of the steps here is a large part of the point of this question. Wonderful. Now that we've applied what we learned about directing groups to synthesis problems, let's think about this final column of the chart, which describes the relative rates of these substituted benzenes versus benzene in electrophilic aromatic substitution reactions. Explain the observed trend in the rate of nitration of the following compounds. Recall that in electrophilic aromatic substitution reactions, the aromatic ring is acting as the electron-rich species, donating electrons to the electron-poor species, the super electrophile, in the rate-determining electrophile addition step. Electron-donating groups will increase the reactivity of the ring. The ring is more electron-rich and thus will react faster in this rate-determining electrophile addition step. Meanwhile, if there's a substituent that is an electron withdrawing group, so if this is a substituted benzene, then we would expect that to decrease the nucleophilicity of the ring. We can think about it having less electron density to donate, and thus slow the rate of electrophilic aromatic substitution reactions. The data here bears this out. Alkyl groups are electron donating. They're weakly electron donating, but they're still electron donating. And so the alkyl benzene reacts faster than benzene itself. Acyl groups are pi electron withdrawing groups. We can recognize it by the adjacent pi bonds. We know that it withdraws electron density out of the ring. Thus, this ring is less electron rich than benzene itself and reacts more slowly than benzene. Can you predict the relative rate of chlorobenzene to these 3 molecules? Where should it go in this sequence? Yes, it should go here. It will have a slower rate than benzene because chlorine is a sigma electron withdrawing group. But it's a pi donor group, and it's not quite as electron withdrawing as acetophenone as the acyl group is. So it'll have a rate of reaction intermediate between benzene and acetophenone. One more. What about these two molecules? What about methoxybenzene and nitrobenzene? Where would they rank in terms of relative rates? Yes, alkoxy has a lone pair of electrons that can be donated to the ring. So it is more electron donating than alkyl. And so it would have the fastest rate of electrophilic aromatic substitution under nitration conditions. Nitro, it has the strongest of these electron withdrawing groups. This is the most electron withdrawing. So it would have the slowest rate. It would be all the way at the end here, the slowest rate of additional nitration. One more question. We've learned that electron donating groups are ortho-para directors and usually react faster than benzene. This is because those rings are more electron rich than benzene. And in general, meta-directing groups, electron withdrawing groups such as nitro or nitrile or acyl, which often have this pi bond adjacent to the ring rather than a lone pair adjacent to the ring. So I drew it out that way just to help you think about it and remember the pattern. Those groups are meta-directors, and usually they're deactivating. And that, of course, is because they're withdrawing, these electron withdrawing groups are withdrawing electron density from the ring, so the ring is less electron rich and less nucleophilic. There is one notable exception to this observation. Can you think about what it is? Dun, dun, dun. Halogens are orthopara directors, but they're also deactivating. Halobenzenes react slower than benzene in electrophilic aromatic substitution reactions. Why? How can we explain that? Well, those halogens are electronegative and they are withdrawing electron density through the sigma framework. And thus, this ring is less electron rich than benzene and thus less reactive with electrophiles. However, despite this, once the electrophile does add to the ring, the halogen can stabilize the intermediate, making it lower energy. Now, this resonance structure might not be very contributing, but it is a little bit contributing, and it does stabilize the intermediates resulting from ortho and para addition. All right, so halogens are an exception to the observation that ortho-para directing groups are activating while meta-directing groups are deactivating. But generally, this trend is true. Yay, we're done. Summarize, but you're not done yet. So we need to summarize and reflect. What did you learn? How is it related to things you already know? And what questions do you have? Really important for today. Everything we talked about is quite related to the last lesson and other lessons that you have had in this class, Organic Chemistry 1, and even General Chemistry. Have we achieved the learning goals? Yes, I believe we have. You should now be able to identify common substituents that we might encounter on benzene rings as electron donating or electron withdrawing. Review this chart. Live it, learn it, love it. Predict the products of electrophilic aromatic substitution reactions of benzene derivatives. You are going to do that because you know the 6 reactions we talked about at the beginning. Yes. You know which groups are donating and withdrawing, and thus you know if they direct ortho and para. The only curveball is a big group that is an ortho-para director might favor para over ortho. No big deal. Check. Now, draw the complete curved error mechanisms. Yes, you can already do that. Explain the selectivity of substitution reactions of benzene derivatives. So was it ortho-para? Was it meta? Using clearly drawn resonance structures and reaction coordinate diagrams. I think you can, but you can go back, use the blank slides, and see if you can reproduce some of these beautiful and amazing explanations from the beginning of the lesson. I hope you had fun. I know I did, and it's time to practice.